Okay, let's dive right in. Welcome to this explainer. Today, we're totally decoding the incredible processing tech that actually makes modern computing and, the massive AI boom we're living through possible. We're going to take a really close look at the exact hardware architectures running our digital world, breaking down how they function, why they were even created in the first place, and how their roles have evolved in ways literally no one originally predicted.
But before we get into the heavy hardware specs, think about this for a second. What actually connects rendering a massive fantasy world in a video game, predicting a chaotic storm system, and training the absolute latest artificial intelligence? I mean, these fields seem wildly different on the surface, right? But the fascinating reality is that they all rely on the exact same underlying hardware revolution to function.
So to uncover what that revolution is, we are going to follow a pretty straightforward roadmap today. First up, the computer's brain. Second, CPU versus GPU. Third, building a 3D world. Fourth, the power of parallel. And finally, GPUs beyond graphics.
All right, let's kick things off with Section 1, the computer's brain, and a quick look at early computing systems.
As you probably know, the CPU, the central processing unit, is the primary orchestrator of a system. It's the brain. Historically, a lone processor had to handle absolutely every single instruction, essentially managing the entire show single-handedly. But as software got exponentially more complex, placing these infinite demands on one single central hub, it became a massive bottleneck. The solitary processor just started getting totally overwhelmed.
And that bottleneck forced hardware architecture to evolve, ushering in the era of specialized co-processors. Think of them like dedicated experts, hired specifically to offload highly specific tasks from the main CPU, just so the overall system could run much, much faster concurrently. The absolute most famous of these? Well, that's the Graphics Processing Unit, or GPU, which stepped in to handle intense visual calculations so the CPU didn't literally melt under the pressure.
Which brings us right to Section 2, CPU versus GPU, a classic tale of the generalist versus the specialist. Now, there is a massive misconception in the tech world that one processor is simply, faster than the other. While GPUs have thousands of stream processors, an individual GPU core actually typically runs slower than a standard CPU core. So you have to be very careful not to blindly declare CPUs as the superior, faster technology, because they were designed with two completely different goals in mind. They have entirely different performance profiles.
The crucial difference really lies in those design goals. CPUs are fantastic all-rounders. They're like a brilliant executive handling intricate, winding logic, but on small datasets. GPUs, on the other hand, well, they act more like a massive industrial factory. They are highly specialized and built to mass-produce simple calculations, things like matrices and vectors, across millions of data streams all at the exact same time.
Let's ground this theory in some reality. In Section 3, building a 3D world by rendering landscapes. Picture your absolute favorite open-world video game. The sheer volume of math required to instantly generate a realistic mountain landscape in full color the second your character turns the camera, it's staggering. It requires a very specific type of mathematical heavy lifting that just so happens to be absolutely perfect for our specialized coprocessor. To really grasp this heavy lifting, look at how a render pipeline works. First, millions of points get X, Y, and Z coordinates. Next, every resulting triangle needs a texture applied to it. Then, dynamic lighting is calculated with specific angles and brightness. And finally, massive arithmetic determines the exact red, green, and blue values for every single pixel from the camera's perspective. The hardware is essentially screaming in this endless loop. For every vertex, do this. For every single pixel, do that. And that brings us to exactly how the GPU survives that insane workload. In Section 4, the power of parallel and SIMD processing. The absolute secret weapon to solving this massive pixel problem is something called SIMD, Single Instruction Multiple Data. See, because calculating the RGB value of one pixel is totally independent of the pixel right next to it, the GPU doesn't have to process them one by one. Acting as a purpose-built SIMD processor, it just applies the exact same mathematical instruction over a massive block of data at the exact same millisecond. We're talking about thousands of operations. While a CPU might win a one-on-one race for a single floating point operation, the GPU is processing thousands of them simultaneously. It absolutely crushes the CPU in this specific arena, strictly due to its bespoke design for parallel processing. Honestly, this is exactly why your gaming rig can output 4K resolution at 120 frames per second without skipping a beat.
But here is the huge twist in our story. Welcome to Section 5, GPUs Beyond Graphics and the GPGPU Evolution.
So before 2006, GPUs were strictly doing what their name suggested, rendering graphics. But then, a massive light bulb went off in the industry. Engineers realized that pushing millions of simple calculations simultaneously wasn't just useful for rendering video game mountains. No, it was the ultimate key to handling any massive dataset, giving birth to general-purpose computing on GPU, or GPGPU.
Today, basically any complex data problem is routed straight to the GPU. Modeling chaotic weather patterns, training the large language models we use every single day, predicting stock markets, oil exploration, or even mapping gravitational fields. If a task requires crushing thousands of data points concurrently, the GPU is the undisputed king. Which leaves us with a pretty fascinating thought. We started with a solitary brain that simply needed a little help putting pixels on a screen. And that tiny necessity accidentally birthed the parallel processing powerhouses that are driving today's AI revolution and our most advanced analytical breakthroughs. So as our datasets continue to literally explode in size and the lines between graphics and artificial intelligence completely dissolve, you really have to wonder, what specialized hardware revolution is waiting just around the corner? Thanks for joining me for this explainer, and keep exploring.